How's it going, everyone? We're going to get started on the latest AP practice problem for the Calculus BC 2020 exam. This just got released yesterday, so we're going to take a really good look at it, and let's not waste your time. Let's get started. So this is a 25-minute question. There are, I think, 7 parts to it, which is again, far more than an actual AP exam. 7 parts in 25 minutes sounds really ambitious to me. But this is just a practice exam, so it may or may not be actually 7 parts once we get to the actual test. So anyways, 25 minutes, 7 parts of the problem, and it's actually, to my eyes, 2 problems mushed together. There's not a lot of coordination between the 2 parts. You'll see what I mean. This is the first part of the problem. You have a line graph, and the graph is the graph of f. And down here at the bottom, we see that g is equal to the integral of f, which means that f is actually the derivative of g. So this is a graph of a derivative problem. If you looked at my FRQ trainer for the graphs of the derivative, then you should be in pretty good shape for this one. Part A, find the average rate of change of g over the interval -2 to 5. So it's an average rate of change problem. We see that pretty regularly. Part B is kind of a strange limit problem. This is also going to test your ability to take derivatives with the chain rule and also L'Hopital's rule. We'll definitely look at that later. Part C, you have for -2 to 5, find all values of x for which the graph of g has a point of inflection. Explain your reasoning. This also comes right out of that FRQ trainer packet. And part D, you have the integral of a derivative. So this is a fundamental theorem of calculus problem. But there's some funny things about it. If you take a look at that, you have f prime of 6 minus 2x. So we'll have to do something special for that. This second part of the problem, you have a graph, a line graph, and it says the function h has derivatives for all orders, for all real numbers x. A portion of the graph of h is shown above, along with the line tangent to the graph at x equals 0. Just a quick pause on looking at this. You can see over with the graph, one curved line and one straight line. So this curved line over here, that's going to be your h, and this straight line, which happens to be tangent at x equals 0, that is the tangent line that they're talking about. Okay, in addition to that, you have derivatives of h evaluated at x equals 0 in this table. And then you also have this region R. So really they're trying to cram a whole bunch of skills here in this one question stem. Let's see. Reading this chart just to make sure you can read it. N is 2, so 3 is h2, 0. So the second derivative of h is 3. And the third derivative of h evaluated at 0 is -23 over 2. So on. The fourth derivative of h evaluated at 0 is 54. You got to know how to read that chart. Okay. So we're going to start by taking, we have to look at these questions. Part E, write the third degree Taylor polynomial. Okay, that's a Taylor polynomial question, which we have been expecting. Part F, write but do not evaluate an integral expression that gives volume of a solid generated when r is rotated about the horizontal line y equals -2. If you're looking at that FRQ trainer for area and volume, I think this occurs in day 1. We prepare for that pretty well. And part G is a weird one. Just like the part D on the previous was a strange one. This one is to evaluate an integral from 1 to infinity. So this is a Calculus BC skill, part G. It's an improper integral, so we'll have to take a limit as we go to infinity. Part A. Let's find the average rate of G over the interval -2 to 5. So any average in integral is going to be an integral. Sorry, any average in calculus is going to be an integral. The trick here is to read this in the correct manner. And the way that you want to read this is, it's not the average rate of change, it's the average rate of change. So you're finding the average of a rate of change. The rate of change of G is G prime. So when you reinterpret that, you're looking for the average of G prime over the interval from -2 to 5. That's really going to make all the difference in this problem. You don't have to mess around with those physics formulas that you learned. This is calculus, and we're approaching this not as an average rate of change. We're approaching this as the average rate of change. Same thing, slightly different way of approaching the problem. Okay, any average in calculus is the integral definition, 1 over b minus a, integral from a to b of f. In this case, we're finding the average of G prime from -2 to 5. So here's our formula with G prime and 5 and -2 substituted in. Well, that simplifies nicely, and we can use the fundamental theorem of calculus to evaluate that integral. The integral of G prime of x is just G of x evaluated from 5 to 2. Now the fun really starts, because what is G of 5 and what is G -2? Well, let's see. G of x was defined as this integral from -2 to x of f of t, which is one way to interpret an integral, and a really important way to interpret the integral, is as the area of the function, or between the function and the x-axis. So we're actually going to look at this as area, which is, in my class, the first way that we started looking at antiderivatives and integrals. When you substitute -2 for x, you get G of -2 is the integral from -2 to -2 to -2, which you learn really early on that that's just equal to 0. G of 5, however, is this integral from -2 to 5, which is the area. So let's take a look at the area. Here's our graph again. You will notice that this region, you can break this up into 3 triangles and one kind of a crescent shape figure. Here's that first triangle. Area of a triangle is just 1/2 base times height, so 1/2 1 times 1. Here's our second triangle. Now this one's a little bit, you're going to have to do a little bit of interpretation. You know that this line, the diagonal one with a positive slope, that's going to cross the x-axis right over here, and that's at 1/2. So the base of that purple region, that's going to be 3/2, and the height's going to be 1. But remember that when we take the integral is going to be the negative of that area. So the area is 3/4, but the integral is going to be -3/4. Our third triangle is going to be this very nice right triangle here. This one's not as bad. The base is 3/2 like before, and the height is 3, so this gives us an area of 9/4. Now take a look at this crescent shape that I haven't highlighted yet. Okay, we're going to start by taking a look at the area of this square, which happens to be 9. The problem was very sure to tell you that this was a quarter of a circle. So we're going to actually take out this green quarter circle region. The area of a quarter circle is 1/4 pi r squared, which simplifies out to 9 over 4. So if you want just the area of that crescent shape, that's going to be the area of the square, 9, minus the area of the quarter circle, which is 9 pi over 4, giving us an area of 9 minus 9 pi over 4. When we put that all together, we get the integral is 1/2 minus 3/4, remember that purple triangle, plus 9 over 4, which was the green triangle, plus 9 minus 9 pi over 4, which was the area of that crescent region. Add that all together and you get 11 minus 9 pi over 4. So G5 is 11 minus 9 pi over 4. G negative 2 is 0. Let's come back to the area formula. Sorry, the average formula. So the average of G prime, where we left off, was equal to 1/7 G5 minus G negative 2. When you substitute that in, you get the average rate of change of G is 1/7 of 11 minus 9 pi over 4. Just leave it like that. There's no need for you to take the extra time to make that a decimal. So that's the end of part A. Let's take a look at part B. Let's find this limit. The first way to approach a limit is to try direct evaluation, because if there's nothing funny going on in the graph, if you substitute, in this case, -1, you should be able to get the limit. So let's substitute -1. It's f of -1 squared plus -1 over f prime of -1 minus -1, which simplifies to this. And we'll take a look at the graph and try to figure out f of 1 and f prime of -1. Here's our graph. There's 1 and -1. And you can see pretty easy that f of 1 is 1 and f of -1 is 0. The one that's a little bit more tricky, and it's really not too tricky, especially if you've been doing maths for a while, the derivative is the slope of those lines. So the slope of the line when x is equal to -1 is -1. Therefore, the derivative evaluated at -1 is -1. And over here, the derivative evaluated at 1 is equal to the slope of this line, which if you just look at rise over run, that's equal to 2. So here are our functions and their derivatives evaluated at 1 and -1. Let's substitute that in. Our numerator is 1 minus 1. Our denominator is -1 plus 1. So that is 0 over 0, which, I don't know, gets me kind of going, because that means I can use L'Hopital's rule. Let's look at L'Hopital's rule. And to use L'Hopital's rule, you're going to take the derivative of the numerator over the derivative of the denominator. Now look at the derivative of the numerator. We know that the derivative of f is f prime, but since we're doing f of x squared, we're going to have to multiply f prime of x squared by 2x. The derivative of x is just 1. The derivative of f prime is f double prime. And the derivative of x is, again, still 1. So that means the derivative, or the limit that we started off with, is equivalent to the limit of f prime of x squared times 2x plus 1 over f double prime of x minus 1. Now again, we're going to try direct evaluation. So we're going to substitute -1 for x. We'll have f prime of -1 squared multiplied by 2 times -1 plus 1 over f double prime of -1 minus 1. So just to refresh your memory, we're going to simplify that again. That's -2 of f prime of 1 plus 1 over f double prime of -1 minus 1. As I was saying, to refresh your memory about what this looked like, here we have our derivatives and our function. The only new thing here is we needed to know the second derivative when x equals -1. Well, when x equals -1, we have a straight line. And the second derivative at any straight line is equal to 0. You could think of it as this. We know that f prime of x is equal to -1, and the derivative of -1 is equal to 0. Now remember what I'm saying. The derivative of f prime is always, f prime of x is always -1 along that line segment. It's always -1. So that means f double prime at -1 is going to be 0. Let's substitute our values in, and we get -2 times 2 plus 1 over 0 minus 1, which is, well, you can evaluate that. That's 3. Therefore, the limit as x approaches -1 of that nasty-looking function, that's equal to 3. Part C. For x between -2 and 5, find all values for which the graph of g has a point of inflection. Explain your reasoning. So for this one, it says explain. So you're going to have to write some sentences down or some phrases down. You got to write something. Here's a definition of a point of inflection. So g has a point of inflection when g double prime changes sign. Of course, g has to exist as well, but we'll put that aside because g is continuous for our graph. So if g double prime has a point of inflection when g double prime changes sign, well, what is g double prime? We knew that g prime was equal to f of x, so g double prime should be f prime of x, which is just the slope of the given graph. So in order for you to evaluate g double prime, you just need to look at the slope of the graph. So when you bring that back to that first statement, g has a point of inflection when g double prime changes sign, that's the same thing as saying g has a point of inflection when the slope of the graph changes sign. So we've just interchanged g double prime with the slope of the graph, which means we should take a look at the graph. I've marked the slope of the graph at each of these segments. Notice that for this first segment over here, we've got a negative slope. For this second segment, the graph has a positive slope. And for this third segment, the graph has a negative slope. Which means that at these 2 points that are highlighted now, the slope of the graph changes either from negative to positive or positive to negative. This occurs when x is equal to 0 and x equals 2. Bringing it back, at x equals 0, the slope of f changes from negative to positive. At x equals 2, the slope of f changes from positive to negative. Therefore, g has points of inflection at x equals 0 and x equals 2. Now you have to write out that entire thing, or at least most of that entire thing, most of it. You need to make the linkage between the graph and g double prime. You need to make the linkage between g double prime and the slope of the graph. I think I just said that. And then you also have to have a linkage between the change in the slope and the point of inflection. And once you link all of those things together, that'll tell you where the points of inflection for g are. I don't even think I can talk about this problem in the 25 minutes allotted, let alone write the whole thing out. This says to me that you should probably do this on paper once you get the chance. So get out your 8.5 by 11 sheets of paper, your lined paper, start writing your name and your AP ID on them. Have them ready to go for the test on Tuesday. To evaluate this integral, let's start with our old friend, the fundamental theorem of calculus. The integral of a derivative is just f of b minus f of a. What we have is the integral of f prime of 6 minus 2x. There's a couple things that are different from what we have in the first line of the page. Most notably, we don't have f of x and dx, we have f of 6 minus 2x and dx. Now those variables, whatever's inside f prime and whatever is the variable of integration, the letter after d, those have to match, otherwise we can't use the fundamental theorem of calculus. So they have to match. The other thing that I did here, which isn't a change, but it's important to emphasize that the upper and lower limit, instead of just saying 2 and 4, what we're really saying is the lower limit is when x equals 2, and the upper limit is when x equals 4. So how do we change the inside of f prime so that it matches with this variable of integration? You've done this before, and it's actually called a u substitution. So we're going to let u equals 6 minus 2x. Some pretty easy calculus tells you that du equals negative 2 dx, followed by some easy algebra. And that tells you that dx is equal to negative du over 2. Okay, so let's substitute that into the integral that we started with, and you get f prime of u minus du over 2, which is negative 1/2 of the integral from x equals 2 to x equals 4 of f prime u du. So we've actually created another problem with this integral, and that's the fact that the upper and lower limits are not in terms of u, they are in terms of x. So we need to change those upper and lower limits to be in terms of u. In a proper integral, when you use the fundamental theorem of calculus, everything is to the same variable. So we have different variables. Be cognizant of that. I'm sure this will show up on your AP test. If not this year, then if I'm talking to you in the future, it'll show up for sure. So can't use the fundamental theorem of calculus yet. So we substitute. When x equals 2, u is equal to, well, you can do the algebra, that's just equal to 2. And when x equals 4, u is equal to negative 2. Those are in reverse order, but it shouldn't make too much of a difference. So we have the integral fully transformed is negative 1/2 the integral from u equals 2 to u equals negative 2 of f prime of u du. Everything looks great. We have u's. We don't have a composite function here for f prime, so we are ready to use the fundamental theorem of calculus. This is just equal to negative 1/2 f of negative 2 minus f of 2. Do you remember what f of negative 2 and f of 2 was? Well, you could go back to the graph and you'll see that's 1 and negative 3. I don't think I'm going to go back to the graph in the video. You can definitely do that yourself. Look at the question. So negative 1/2, 1 minus 3, that's just equal to 1. The integral from x equals negative 2 to x equals 4 of f prime 6 minus 2x dx is equal to 1. And that's just the first part of this question. So they're really throwing everything at you with this question. Quick review of the second part. Part E, let's write the third degree Taylor polynomial for h. I always recommend, if when you're writing out a Taylor polynomial, you just start off with the recipe, is what I like to say. The recipe for a Taylor polynomial. That's f of c plus f prime of c x minus c plus 1 over 2 factorial. Everyone forgets the factorials. Don't forget them. F double prime c x minus c squared plus 1 over 3 factorial f triple prime c x minus c cubed. So we're not using f, we're using h, so we've replaced all the f's with h, and We've also replaced all of the c's with 0 because that's what this means right here. About x equals 0. That means the c, the center of this Taylor polynomial, is 0. So this is our Taylor polynomial so far. The only thing that's missing, I also simplified 1 over 3 factorial into 1/6. I'm sure that you're okay with that. The thing that we now need is values for h of 0, h prime of 0, h double prime of 0, and h triple prime of 0. So let's take a look at the given information. Here we've highlighted what x equals 0. And at x equals 0, we know that h of 0 is 3. Now, h prime of 0 is just going to be the slope of that tangent line. Look how genius that was. What is the slope of that tangent line? We'll just use rise over run. You'll get -2. So the slope of the tangent line is -2. H prime of 0 is -2. We're going to look at the chart now. H double prime of 0 is 3, and h triple prime of 0 is -23 over 2. There we go. H of 0 is 3, h prime of 0 is -2, h double prime of 0 is 3, h triple prime is -23 over 2. Just substitute those into our formula, into our recipe, and you get this, which is actually the correct answer. You don't need to do anything else to this. Just leave it the way it is, especially since the time here is going to be a real issue. I simplified it just because I have nothing better to do. But these are both the correct answers. Again, I don't recommend you simplify it here. If it's just multiplication, they'll read with you and you're good to go. So that's part E. If this is actually what the AP test is going to be like, this is the simplest AP Taylor polynomial question they possibly could have come up with. So, who knows? Part F, write but do not evaluate an integral expression. That gives the volume of the solid generated when r is rotated around the horizontal line y equals -2. We prepare for this pretty well, I think, and I personally think they're always doing you a favor when they give you a washer cross-section. And make no mistake, this is a washer cross-section. Y equals -2 is not a boundary for the region R. So as soon as the axis of rotation is not a boundary of the region, you're going to get washer cross-sections. So the volume is equal to the integral of the area, and the area in this case is pi r squared minus pi r squared. Here's our graph. I've notated the axis of rotation in its approximate location, or about as close as I can get without running off the page anyways. The only thing we need here are the radii. So here's the large radii. It's the distance between the curve that's furthest away from the axis of rotation and the y-coordinate of the axis of rotation, which is h minus -2, which you're going to simplify that as h plus 2. Small radius, lowercase r, that's the difference between the y-coordinate at the closest part of the region to the axis of rotation. Now off to the side, I found the equation of that line. Shouldn't be too difficult. You know the y-intercept is 3 already. You had to have computed the slope by now. You know the slope is -2. So the equation of that tangent line is -2x plus 3. Minus that -2, be wary of the grouping symbols here. They could definitely do you in. So here's our lowercase r, our small radius. When you substitute those into the volume formula, you get something that looks like this. The volume is the integral from 0 to 1 of pi h plus 2 squared minus pi -2x plus 5 squared, and you're done. You don't have to evaluate this, especially since you don't know the equation of h. I can envision someone trying to stick a Taylor polynomial in there for h and then trying to evaluate it. Don't do it. Read the directions. Write. Do not evaluate. And that brings us to the very last part of this problem. We've been talking now for about half an hour. And that is evaluate this infinite integral, improper infinite integral. I always like to start off with the antiderivative of the situation. Let's take a close look at that function. In terms of the integral, p is constant. What I'm saying is we're integrating x, we're not integrating p. So this is actually just a power rule integration. Make sure you interpret that as x to the negative p plus 1. And like I'm saying on the slide, that grouping symbol is really important. So don't forget your grouping symbols. It's just a power rule integration. It's 1 over the new power multiplied by x to the new power. The new power is the old power plus 1. Again, those grouping symbols are going to save you. I have a plus c over here at the end because this is a antiderivative and not a definite integral, so got to be proper. If you simplify that, you get negative 1 over p x to the p plus constant. Cool. Now we can do this infinite integral with a little bit more ease. Here's our infinite integral. And the correct way to do an infinite integral is to substitute the upper limit with a dummy variable and take a limit as that dummy variable goes to infinity. We're going to use b for our dummy variable because the infinity appears as the upper limit. Since we have the antiderivative, we're just going to evaluate the derivative from 1 to b. And we're going to take a limit again as b goes to infinity. Substitute those limits just like you would for any definite integral, and you get the limit of negative 1 over p, b to the p, minus negative 1 over p times 1 to the p. Now let's take a look at these. The limit really only applies to this first part of the antiderivative. And we also had to make sure we're substituting in the correct place. We're substituting for x because our integral of, or our variable of integration was x. So anytime you see an x, you're going to put a b. So that's why we have PBP. And what happens when b goes to infinity? Well, when b goes to infinity, p is constant, and the denominator is just going to increase without bound. So this first part, this limit, is 0 because the denominator grows, the numerator stays the same. The second part over here, let me go back. The second part over here, well, 1 to the p power, remember p is constant in terms of this problem. So 1 to a constant power is just 1, and 1 times p is just p. So we have 0 minus negative 1. Sorry, 0 minus negative 1 over p, which is just 1 over p. So this infinite integral is going to eventually be equal to 1 over p. Or I should say it's going to approach the value 1 over p. And that's it. That's a really long problem. It took us, gosh darn, 34 minutes and 7 seconds to get this done. So good luck to you. I think this is the last practice problem we're going to see before the AP test. Get your 5 and leave a comment if I helped you get a 5. I'll see you guys later.